So we've handled so far the first two questions that we have to handle in this section, namely, what type of study design is it? And I've told you to first make the decision between observational experimental studies, and then how we're going to analyze the data that come from these study designs. And I focused you on mostly how we analyze two types of studies, the case control study and the cohort study. I now want to turn our attention for the rest of our time in epidemiology to answering the two remaining questions, namely, what kind of bias, if any, is in this research study? And then secondly, how would you fix the bias? All right, now let me frame this discussion. The first thought you should have when you read any research study is there bias? You never make an interpretation of the results until you decide that the way the study was conducted was clean and that therefore the results are reasonable and therefore can be interpreted. The first thought you should have in any exam question, whether presenting with a research study, therefore, is there bias? Is there something wrong? However, it's not enough to simply know there's bias. You're physicians. And as physicians, you're not just supposed to detect problems, you're supposed to know how to solve the problems. So the second question, how do you fix the bias, is an essential component to this discussion. As we move through this material, I'm going to try to get you to recognize bias when you see it, but then also connect it to the solution. That's an essential learning to make sure you can answer the questions appropriately. But let's begin our discussion by making sure everybody's clear on the basic terminology. What do we mean by bias? That's easy. Bias means deviation from truth. We're doing in our measurement is trying to get as clear a picture of reality as we can. When we do match reality, that's good. When we don't match reality, that's bias. Remembering, the research data we have is not actual reality, it's simply our best measurement and approximation of that reality. The worse the approximation, the more bias. We talk about how good we are at estimating reality by two basic concepts, reliability and validity. Reliability means consistency. Same result every time. We also sometimes use the term precision, but that doesn't seem to be as intuitively appealing to most people as the simple term consistency. Suppose I gave you a test today to see how well you're going to do in your Step 2 CK, and it said you were going to score 80%, good score. And then I gave you a test tomorrow to see how well you're going to do in your Step 2 CK, and it said you're going to score 30%. Aren't you bothered by that difference? Well, that's a lack of consistency. In short, a lack of reliability. Validity is something altogether different. Validity means not only that you're measuring consistently, but you measured what you say you're measuring. Validity is simply accuracy, hitting the bullseye, hitting the target that you've aimed at. If there's something I'm measuring, if I do measure what I want to, that's what validity is about. Now, it's important that you understand and be able to discriminate between these meanings for reliability and validity. And so to try to clarify your thinking, I'm going to fall back on the classic two-target example. Here we have two targets where I'm going to take shots. I'm first going to take shots with my rifle at the target on the left. That's my shots at the target on the left. Is that very reliable shooting? Answer, well, yes, it is. What it's not is valid. I've clustered the shots. They're consistent, but I've missed the target. I'm consistently off, but at least I've clustered them in the same place. This is an example of reliability, yes, but validity, no. As compared to, in this second illustration, I've now clustered the shots, good reliability, but I've also hit the bullseye. That's good validity at the same time. Please note, you can have great reliability and having no validity whatsoever. Please note, if you have good validity, you must first have reliability. In the language of logic, we say reliability is a necessary but not sufficient condition for validity. That is, you have to have it, but just because you have it doesn't mean that you're valid. Validity implies reliability. Reliability makes no implication at all about validity. With those terms defined, we're now going to walk through talking about different types of bias. Now, process is as important as content here. I've worked with a lot of students that seem to have learned the content well. We talk about types of bias. They can tell me chapter and verse about what each one is about, but when confronted with an exam question, they can't pick out the right answer. As I've tried to analyze what's going on here, it looks to me like the problem is you're going too quickly to get the answer before you're doing the right thought process to lead you to the answer. So let's talk thought process. The way you're going to answer these questions in terms of what type of bias is as you read down through the question, something in your head is going to say, wait a minute, something's wrong here. And then you're going to say, this is what's wrong. And finally, and only at this point, are you going to leap to grab out the name and say, what we call this is blank bias. I'll do that again. Something's wrong. This is what's wrong. This is what we call it. That sequence is essential. Those of you that want to read the question know the answer. That happens rarely. Occasionally it does. Congratulations, but usually it does not. It's your process to build from the question to think through to the answer that makes all the difference in whether you get the question right or not. Once again, something's wrong. This is what's wrong, and this is what we call it. I'll try to illustrate that as we go through our examples. I remind you again at this point that it's important that you know the bias types, but also the best solutions. It's not enough to simply know something's wrong. You have to know how to fix it. We have a list of types of bias here. Let me walk down through the list, trying to talk about the different ways these might appear and getting you to practice that thought process I just laid out. The first on our list is called selection bias, or also called sampling bias. These are usually treated as synonyms. Selection bias, sampling bias, the people that are in your study are not a random independent sample of the people in the general population. So when I want to generalize from who's in my study to the rest of the population, I have a difficult time with that logical transition. What I need in order to not have sampling bias is that who's in my study should be a good match for who's outside. Who's in should match who's out. Let's try to give you some illustrations and see if you can detect the sampling bias. I want to do a study trying to get a sense of how fit people are who live in this area of the city. I want to get a sense of their cardiovascular fitness. So to do that, I hire 5 staff members and set them up with some measurement paraphernalia outside of 5 local health clubs. Their job is to assess the cardiovascular fitness of people that come in and out of those health clubs over a 2-week period, then bring the data back to me, and I'll use the data to assess the cardiovascular fitness of the general community. Well, wait a minute. Come on. Isn't something in your gut saying something's wrong there? And what's wrong? Well, obviously, the people going in and out of health clubs are not a good representation for the community taken as a whole. And third step, what do we call that? We call that sampling or selection bias. Something's wrong, here's what's wrong, here's the answer. That's the simple thought process going forward. Let's try another illustration. When I was down in Houston, Texas, about 8 years ago, I was able to go to all the hospitals in the Houston area to give me access to their hospital discharge record for a period of about 10 years. Using that information, I looked at diagnoses associated with and treatments related to tuberculosis. And using that data and a fairly complicated formula, I derived an estimate of the prevalence of TB in the Houston metropolitan area. Question, did I get a good estimate or a poor estimate? Well, I got a terrible estimate. The problem here is so basic it has a name. It's called Bergson's bias. Using medical records to estimate population prevalence is simply a, stupid idea, because it assumes that the people who come into the hospital are in some sense a random template of the people out there in the general community, and we know from experience that's usually not the case. That said, you're going to find this kind of sampling bias, Bergson's bias, in a variety of circumstances. For example, many years ago in Chicago, the head of public health held a press conference just in time for the nightly news. He got up and made an announcement. He was very pleased with himself. He said, "We're beginning to beat tuberculosis here in Chicago." When questioned on how he could make that assertion, he held up a nice, brightly colored chart and said, look, each of the last 10 years, the number of TB patients we treat at the local county hospital has gone down, suggesting that's a good thing. He's making the untenable assumption that the people come into the hospital are somehow a representation of who's outside the hospital. And here's another possibility. Maybe they're just not coming into the hospital anymore. Maybe we have the exact same cases we had before, but we're simply not seeing them. Assuming who you got represents who's out there is a sampling bias problem. A third kind of sampling bias is non-respondent bias. Non-respondent bias, the people that agree to, that is, volunteer to participate in your research study, turn out to be very different than the people who refuse, that is, will not, when asked, participate in your research study. Now look, this non-respondent bias, this so-called volunteer effect, is only a problem when we have volunteer subjects. No volunteer subjects, we don't have a problem here. When do we have volunteer subjects in medical research? Yeah, right, always. Unless they volunteer, we're not allowed to have them in the research. Everybody that participates in medical research is a volunteer, which means what? The volunteer effect is always a problem. Ask yourself, who signs up for these long-term, multi-year cohort studies? Somebody once suggested the same people that show up for jury duty, and we know in a representative sample that isn't of the population. Anytime you're trying to follow people long-term, anytime it requires a lot of participation, you're not going to get a clear general sample of the population. You will have a volunteer effect. You will have sampling bias. So what's the solution to sampling bias? What are we going to do to fix this so it doesn't trouble our research? Well, it's a complicated situation, so we have a complicated fix. It's a two-level intervention. First and foremost, you're obligated to get as good, as complete a random sample as you possibly can. You're going to work hard to reach out and to grab parts of the community where otherwise you wouldn't actually be able to access them. If it's hard, that's okay. Work harder to access that part of the community. But even if you try your very best to try to get all the community participating in the research, you're unlikely to be successful. And so the second part of the fix is we weight the data that we have to make it, after the fact, match the population out there. So quite simply, let's say I know from census data that in this community, half the people are white and half are African American. And in my research study done in the same community, I look at my data and I find out that 70% are white and 30% are African American. Clearly, we have a sampling bias problem. The first thing we should do is roll up our sleeves and go out in the African American community and try really hard to recruit more African Americans into the study. Let's say we do that, we try hard, we put money and effort into it, and now we've gotten it so we have 60% white and 40% African American. We're better, but we still haven't solved the problem. What brings us all the way home is we're going to do after-the-fact weighting of the data. Concretely, we're going to treat that 60% white as if it's 50% white. We're going to treat that 40% black as if it's 50% black and do our analysis on that basis. We're going to make the percentages of who's in match the percentages of who's out. This is called weighting or a post hoc adjustment to the sample. The solution to sampling bias is first, as good a random sample as you can get, and secondly, making sure that the people in the study match the demographics of the people outside. Let me now talk about measurement bias. In measurement bias, the sample's okay. The problem is how I get data, how I get information from the sample. The problem is that the way I gather the information distorts the information that I gather. The method of gathering by itself causes a distortion in what I'm able to glean, what I'm able to take in. Now, sometimes measurement bias is really easy to see. For example, if I was interviewing somebody who was just coming out from talking to their primary care physician, and I say, "Hi, I'd like to ask you a few questions." "Okay," she says. Question 1, "You like your physician, don't you?" She says, "Yes." "Okay." Question 2, "You think your physician's wonderful, don't you?" "Yes." Well, those are so-called leading questions, suggesting the way the question is asked, the tone, the word choice, the nonverbals, suggesting what the answer ought to be. You didn't really find out what her opinion was of her doctor as much as, well, the bias I had as I was pushing the answer on her. Those kind of leading questions are a clear source of measurement bias. But a much more important source of measurement bias is much more subtle. I refer, of course, to the Hawthorne effect. The Hawthorne effect was discovered, of all places, in Chicago. In the 1920s and 30s, some bright young researchers from Yale and Harvard showed up, knocked on the door of a factory manager, and said, "Hey, let us do research here in your factory. We'll tell you how to make people more productive, more productive." Let me translate that for you. They'll work harder for less money. Guy that ran the factory said, "Sounds good to me, come on in." And he gave them a room off to the side of the factory where they could set up their own freestanding production line to see what would make people well, frankly, more productive. The first thing they did was tinker with features of the physical environment. And the first physical feature they tinkered with was illumination. Gradually, day by day, they made the room brighter and brighter and brighter, up to the brightest noonday sun. Then they looked at production records. What they found was that as the room got brighter and brighter, productivity went higher and higher and higher. Wow, they said, we're on to something. Make the room as bright as possible, you get the most work out of people. Well, they're at least pretty good researchers, so before they published that, they tried one other thing. They reversed the process. Gradually, day by day, incrementally, the room got dimmer and dimmer and dimmer, down, by one account anyhow, to about the level of bright moonlight. And then once again, they looked at production records. You know what they found? As the room got dimmer and dimmer and dimmer, productivity went higher and higher and higher. Oops! Clearly, it's not the lighting here. Because when the lighting goes up, productivity goes up. When the lighting goes down, productivity still goes up. If it's not the lighting, what is it? Well, if you're ever trying to decide a source of bias in a research study, here's a strong recommendation. Put yourself mentally, or if you can, physically in the position of a research subject and look around and think about what they might be responding to. Okay, so the four of you here in the front row, you're all doing basic assembly work in the factory. You're making telephone switching components for which you're getting paid. Now, one day, for reasons that are not clear to you, some young white males wearing long white lab coats carrying clipboards start to walk around, watch what you're doing, and take detailed notes on your behavior. What effect might this have on what you do? Right, this is the Hawthorne effect. The fact of observation by itself changes what's observed. This is nothing more than the social science variant of the Heisenberg uncertainty principle. Measuring the electron changes the electron. Measuring you changes you. So what's the solution here? Because, folks, if the very fact of measurement itself biases, what are we going to do? Because we have to measure. The solution is clear. Have a control group. The control group will get measurement just like the treatment group gets measurement. And so even though measurement might distort the results, the measurement is a constant. It will not distort the comparison between the two groups in my research study. As long as we have a research study where we have an intervention group and a comparison group that allows a simple comparison, we have a simple solution to measurement bias. That also tells you on your exam question, if they say what's the source of the bias and you're thinking measurement bias and you notice there is a control group, pick something else. Why? Well, because if the solution's in place, the problem is not there. The next type of bias you need to be aware of is called experimenter expectancy. This is the discovery that what the researcher expects or hopes to find is usually what they do find in the research. We've demonstrated this experiment expectancy effect in a now classic study. We'll come into a grade school class at the very beginning of the school year, and we give all the students a test. Now, folks, the test is garbage. It measures nothing. But we tell the teacher that based on this test, this side of the class, well, has great potential. And this side of the class, well, they're just average. Then we walk away, doing nothing more. We wait and come back about 6 months to a year later, and we pull all the grades. And you know how this ends. You know who got all the good grades. The high potential side of the class got all the good grades. But then, here's the kicker. Now we give an objective-based competency test. A test that assesses not the teacher's evaluation, but objectively what the students actually learned. Any difference between the two sides of the class? Absolutely yes. The high potential side of the class not only got all the good grades, they learned more. Now, why did they learn more? Well, the experiment expectancy effect has its impact not at the level of evaluation, but at the level of interaction. Let's think this through. The teacher was told these are the high potential students, and so, as you watched her, you would see she spent more time with these students, was more encouraging, offered more explanation. She simply gave them more attention. And when she tried an explanation that didn't work, well, these are the bright students, so she tried again and found something until she could get through. The other half of the class, well, these students were okay. She did her job, but she didn't expect much out of them. And so she spent less time, was less encouraging, provided less attention. And when she tried an explanation and it didn't work, well, these are the dumb students, so what do you expect? And she didn't really try more. Can you understand how this can really screw up your research results? Just how you treat the subjects has a lot to do with what the outcome is. And so, what's the solution to experiment expectancy? Well, we've already mentioned this. The clear solution is double-blind design. If the subjects don't know if they're treatment or placebo, and the researcher doesn't know who's treatment or placebo, then they can't act to each group differently, and therefore cannot distort the results by the way they act to people going forward here. What's the solution to experiment expectancy? Double-blind design. Lead time bias is next. Lead time bias is not really about the kind of clinical trials we've been talking about. Instead, it's an issue when we're doing screening, trying to show benefit from early screening and detection in a medical setting. The problem is we sometimes think we're doing good and we actually haven't done any good because we're looking at things through a distorted prism. Let me try to lay this out by walking through a series of 3 scenarios with you. A is the baseline scenario. At 0, the patient gets the disease. At DX, we diagnose them with the disease. And then death along this timeline is when they traditionally die. That's the baseline we're starting with. And then, scenario B, we start an early screening and detection program. The patient gets the disease the same place, 0, but now you'll notice we detect it much sooner than we did before. Of course, the patient dies the same place they always did. So clearly, there's no benefit here. But if we're not careful, we're going to think there's benefit. We're going to think there's benefit because there's a metric physicians love to use, namely, how long does a patient live after diagnosis? If I'm using that metric here, I would say in scenario A, well, the patient lives on average 5 years after diagnosis. But now, with a new advanced screening program, the patient lives 8 years after diagnosis. See how much good we've done? Yeah, we've done no good whatsoever. The patient's dying the same place they always did. In fact, you could argue we've in fact done bad because now the patient is worried about the disease 3 additional years when before they were at least blithely unaware. Real benefit of screening is scenario C. The patient gets the disease at 0, where they did before. We diagnose it earlier, as we did before, but now you'll notice the patient lives longer than they did at baseline. This is real benefit of screening. Not finding out sooner, but living longer. What's lead time bias? Easy. It's confusing early detection with increased survival. It's confusing what we call front-end detection with back-end survival. What's the solution to lead time bias? It is stunningly simple. Simply throw out the metric of how long patients live after diagnosis and never use it again. Better would be to use the metric we've talked about previously, life expectancy. Let's look again at scenario B and scenario C. Scenario B, you might say, for example, the patient's life expectancy is age 74. But now, scenario C, with our early intervention treatment program, now the patient's life expectancy is 77. That's not a misperception. That's clearly 3 additional years of survival. What's the solution here, once again? Get rid of the metric of how long patients live after diagnosis and use the more appropriate metric, life expectancy. Recall bias is next. Recall bias is fairly easy. In recall bias, we ask people, subjects, patients, about things in their past, and they simply tell us information that's incorrect. Now, if we ask people about the past and they say they don't remember, that's not bias. That's called missing data. And although missing data is bad, it's not bias. It's a lack of information rather than bias, incorrect information. Recall bias happens for 2 reasons. First, patients think they remember, but they actually don't. So, think with me for a second. Think back. You remember what life was like when you were 13 years of age? Can you remember that? You remember how things were when you're 13? I'll answer that for you. No, you don't. Because what you tell me today about being 13 and what you'd have told me when you were actually 13 would be 2 very different things. And if I were to try to understand being 13 based on what you tell me as an adult, I'd have a very distorted view about what that adolescent period was actually like. Second issue. Patients, when they're asked by authority figures such as physicians what happened in the past, feel compelled to come up with an answer. Even though they don't remember, they feel like they need to have an answer. This is called a demand characteristic. An authority figure asked, we feel like they're demanding an answer from us. In these circumstances, patients often just make crap up just to provide an answer. We write it down as if it's true when in fact it's absolute fiction. Think for a second. Think back, December 13th last year. What do you have for lunch? Well, if you say you don't remember, okay, that's missing data, but suppose you tell me you had soup and sandwich, and I write down soup and sandwich. Now, maybe you didn't, and what you just did was answer my question based on what you think was a good answer. What you gave me was pure fiction. But what also happens here is now you've given me that answer, you're likely to believe that what you said must be true, because you're not someone that would lie to the doctor, are you? So what you said must have been correct. If I would give you a lie detector test, you would pass, because you actually believe that what you made up is now actually correct. This is recall bias. Recall bias, patients simply don't remember what happened in the past, and so when we get information, it's distorted, incorrect information. What's the solution to recall bias? Easy. Solution is two words, they mean the same thing: confirmation or triangulation. All this means is we must get independent sources to see if we get the exact same information. If we do, we can believe what it is we got. If we don't, then we can't believe what we got. Now, what type of study is most vulnerable to recall bias? That should be easy. That should be the case control study, right? The retrospective study. Since we're trying to get data from the past, this is the study that's most vulnerable to this particular kind, recall bias. Since we're talking about case control, let's switch over to talk about cohort study. What's the most likely kind of bias we may encounter in a cohort study? Well, a number are possible, but the most likely is probably selection bias, sampling bias, because getting in people to stay in the study across the long cohort study is relatively difficult. Main bias for case control study is recall bias. Main bias for cohort study is probably selection bias. Next up, we have something called late look bias. And this is, again, a little bit different than the classic study designs we've been talking about. Late look bias, you're trying to get a sense, you're trying to characterize some severe, maybe life-threatening disease. The problem is the most severe cases won't be available to you. They may be dead or in some other way non-accessible. And so the picture you get of the disease is biased towards the healthier end. You get the least sick people and therefore a distorted picture of reality. Concretely, over the last several years, I've been traveling around the world trying to get a sense of the actual symptoms of AIDS. To do that, I've talked to every AIDS patient I can find all around the world. At the end of this enterprise, I discovered, looking over my data, that the symptoms of AIDS are, actually fairly mild and not all that debilitating. Why would I reach that conclusion? Because the most severe cases are either dead or so demented that when I try to talk to them, I can't actually access the information. This is late look bias. The most severe cases are gone. I've looked too late to see them. Late look bias. What's the solution to late look bias? Well, that's simple. We talk about stratify by disease severity. What we mean here is to make sure I get representation across the natural history of the disease. Not merely the easy-to-access cases, but the harder-to-access later stages as well. I need to, in short, make sure I don't simply talk to AIDS patients, but we talk about 4 stages of AIDS. I need to make sure I have representation across all 4 of the stages in the progression of AIDS. Confounding is next. Put a star by this one and pay it special attention, because confounding is a little slipperier than the others. In confounding, things are wrapped up together so you cannot parse them apart. So in a well-run and well-designed research study, there's one and only one difference between the intervention and the control group, namely intervention versus not. Everything else has to be constant. Because of that one and only one difference at the outset, any difference that occurs as an outcome in the study must, by simple pure logic, be due to the difference I started with. But suppose there's more than one difference at the outset. Then any difference I find as an outcome could be due to any one of the differences I started with, or indeed the combination of all of them together. This is confounding. Confounding is, in short, not an argument about what results I got. It's an argument about why I got those results. In confounding, the results are clear, but we're having a debate about what produced or made those results happen. Here's the bottom line. Every study is confounded. I don't care what prestigious journal published it, every study is confounded. It's simply humanly impossible to rule out all the competing explanations or all the competing factors that might influence the research results. Well, if every study is confounded, what then is the solution to confounding? Once again, for a complicated phenomenon, it's a two-level intervention. Level one, you're obligated to try to do as good a job as you can having a good research design and conducting your study appropriately. In short, we're going to do everything we can, shoulder to the wheel, to reduce confounding as much as possible. But you'll never purely succeed. So the real solution to confounding comes as we look at the combination of all the research studies that are out there. The real solution to confounding is do multiple studies. Now follow the logic here. Since every study is confounded, but most studies are confounded in a different way. Therefore, the aggregate, the generalized weight of all the studies taken together creates a lens by the common areas in which we can see clearly what reality is. What's the real solution to confounding? Do multiple studies. Have you ever heard the phrase, the definitive research study? You ever hear that phrase? Well, you understand there is no such creature. Anyone that's looking for the definitive research study doesn't know what they're talking about. Since every study is confounded, there can't possibly be a definitive research study. It's the weight of the evidence that gives us our clear picture of reality, not any one study by itself. Finally, I want to talk about one additional kind of bias, design bias. The problem is not about who's in my study. The problem is the way I combine the pieces of my study to get the results that I get. Remember, it's sampling bias. The problem is who's in my study doesn't match who's out in the general population. In design bias, the most common problem is something called non-comparable control group. That's a technical way of saying the people in one arm of my study, the treatment arm perhaps, are not the same kind of people as in my comparison arm. If I have different kinds of people, that alone could give me differences in the comparison, as opposed to differences due to the intervention itself. You're going to hear the word randomized relating to research in two different ways. First, we talked about it from a sampling bias point of view, where the solution is to do random sampling. Go out in the population and gather, as well as you can, a generalized sample from the population. But now we have a different kind of randomization. Here the randomization is about who goes into the treatment or the control condition. The solution to design bias is random assignment. That is, whether your treatment or whether your control is a result of this random process we talked about before. Random sample is how I get the generalized pool of people to be in my study. Random assignment is how they end up in the treatment or the comparison arm of the study. All of these types of bias are things that distort, confuse, and frankly, render our great research efforts sometimes useless. Your first thought when confronting a research design described in a test question is just here. It's supposed to be to think about and reflect on what type of bias might be present. If they say, what should the researcher conclude from this study, and you decide it's biased, then the right answer is, the study's biased, no real conclusion is possible until the bias is fixed. Let me end this by one just general oral question, have you think through and try to apply some of the kinds of bias that we've talked about. I want to do a research study where I am trying to get a sense about the risk factors that lead to people having MIs, myocardial infarctions. My research design has me being notified by all the emergency rooms in a certain geographic area when they have a patient who comes in after an MI. I'm then going to send my staff over and we're going to interview these MI patients and get a sense of what their historical lifestyle factors are. We're going to have a comparison group of people that come in with other trauma injuries not related to MI, so we have a clear comparison group in place so we can have a reasonable, expectation of getting a sense from the comparison about what are the key factors for MI just as opposed to key background health factors. What is the problem in this research design? Well, let's see. Recall bias, You could argue recall bias, but since I'm asking the patients who are the MI patients to recall things in the past, I'm asking the other trauma patients to recall things in the past, that's going to be equilibrated. So I don't think that's going to give me distortion here. The real problem we have here is late look bias. The real problem we have is that 1/3 of MI patients die before they make it into the emergency department. And so I won't be able to talk to them, won't be able to interview them, won't be able to get any information about the risk factors that might be in their past. And by the way, aren't those the patients we probably most want to talk to? Aren't they the ones that are most likely to, well, let's try that again. Aren't those the patients that we most want to get information about? They are in some sense the sickest, and they won't be included in the study. This is late look bias. They've died. We've looked too late. To conclude this section, let's turn our attention to the review questions at the end of the chapter. I'm going to look at question 36 to 41. All these questions come from the same table: disease, well, exposed, non-exposed. Now, the interpretation of this table will differ based on the questions that we're confronted with. And this is because we're giving a question sequence, not the way the real USMLE Step 2 CK works. There you only get one question per table, but just for way of making sure you're thinking clearly, let's use this as a way to test your knowledge of the content. First, the question says, 36, assume the table represents a cohort study. What is the incidence rate in the exposed? A cohort study. What is the incidence rate in the exposed? Well, the question targets us to only the exposed group, not overall, just the exposed group. Do we have how many total people there? 695. How many diseased people do we have? 520. So the answer there is A. 520 divided by 695 is the incidence rate in the exposed group. Next up, assume the table represents a cross-sectional study. What is the relative risk? How do we do a relative risk calculation from this table? Well, the way we do the relative risk calculation would be to take a ratio of two incidence rates. All right, next let's do question number 37. Question 37 says, assume the table represents a cross-sectional study. What is the relative risk? Well, to do relative risk, I have to take a ratio of two incidence rates. We have a problem here, however. The problem here is it says cross-sectional study. Because this is a cross-sectional study, I have no incidence rate whatsoever here. The right answer, therefore, here is I. Given no incidence data, I simply cannot compute a relative risk. If this were, by contrast, a cohort study, then I could compute a relative risk, which I would do by taking the two incidence rates, 520 divided by 695, compared to 80 divided by 305. But please remember, since it says cross-sectional study, don't do that. The right answer here is I cannot be determined for this type of study. Question 38. Assume the table represents a case control study. What would I do for the odds ratio? Well, that should be fairly straightforward here. It's going to be, again, AD divided by BC. That would be 520 times 225 divided by 175 times 80. In other words, letter G is the best answer here. Number 39. Assume the table represents a cross-sectional study. What is the prevalence of disease? Well, let's see. Can I get prevalence from a cross-sectional study? Of course I can. Remember, a prevalence study is basically a synonym for a cross-sectional study. As always, we're going to get the prevalence in the marginals. So in this case, it's going to be letter B, 600 divided by 1,000. Next, question 40. Assume the table represents a disease outbreak investigation. What is the attack rate for the people who did not eat the food? Attack rate for the people that did not eat the food. Remember, an attack rate is merely a type of incidence rate. So what I need here is an incidence rate for the not eat the food, the non-exposed. Therefore, 80 divided by 305 is the answer, therefore E. And finally, assume the table represents a cohort study. A cohort study. What is the attributable risk? First, can I do an attributable risk from a cohort study? Yes, I can. Relative risk or attributable risk. What's the mathematical operation I'm going to do with an attributable risk? That's easy. Subtraction. And so right there, you have the answer. It must be H. 520 divided by 695, the first incidence rate, minus 80 divided by 305, the second incidence rate. The answer to that one is H. And with that, congratulations, ladies and gentlemen. We are done with epidemiology.